So system of particles, this is session number 8. So just going through a recap of the last lecture's notes and things. So we discussed about perfectly elastic head-on collisions, inelastic head-on collisions, and of course perfectly inelastic collisions. And the general formulae for these type of collisions. We'll take a quick recap of that. And then we are going on to discuss about the collision of a rigid surface or a fixed rigid surface. A particle coming and bouncing off or colliding with a fixed rigid surface, that kind of situation also we discussed about. So let's take it from that one. So first of all, let's take a quick recap of the formulae for the general formulae for head-on collisions. Okay. So if before impact, the velocities of m1 and m2 with this kind of sign convention are u1 and u2. Then during impact, they apply collision impulse equal and opposite on each other. And as a result of that, let's say the final velocities are v1 and v2. So two approaches. One is we can apply the principles and get equations from that. So conservation of momentum will be one equation. And the coefficient of restitution as a definition will be the other equation. So we have this initial momentum is equal to this final momentum. And we have from this we can generate an equation like this, that v2 minus v1 is coefficient of restitution times u1 minus u2. So this is one approach that we can take. We can always start by writing these two equations and then solving them simultaneously. Or we can take the approach that we have the ready-made formula which comes to solving these. And as I told you, there is some merit in trying to memorize these formulas so that we can use them directly in questions. Also helps us with the analysis. So these kind of formulae. Just to discuss few special cases of this in the above formula. If the coefficient of restitution is 1 and the masses are equal, so that is if we are taking a case of perfectly elastic collision of identical masses. Then we get the situation that V1 becomes U2 and V2 becomes U1. So they exchange their velocities. So that is one important special case that you can see directly works out when you substitute these two conditions in the formula, that the masses are equal and coefficient of restitution is 1. So one set of diagonal terms becomes 0, these two terms, and these two terms become unity. So V1 becomes U2 and V2 becomes U1, which means that they exchange the initial velocities. And another important case you can keep in mind, which will if E is equal to 1 and U2 is 0, that is perfectly elastic head-on collision of a moving body with a stationary body. Then V1 becomes M1 minus M2 upon M1 plus M2. U1, and V2 becomes 2M1 upon M1 plus M2. U2. So the important thing now is that in this case, you can see that if the colliding body is lighter, if M1 is less than M2, then V1 is negative. So it recoils. It returns back with a recoil velocity. Whereas if the colliding body is heavier, that is M1 is greater than M2, then V1 is positive, which means that it does not recoil. It continues in the same direction. So these are two special cases which are worth keeping in mind, because when you are solving collisions as part of larger problems in physics, as part of a bigger overall problem, then this is just keeping in mind, this thing will help you out with having some idea about what is happening in the given question without getting into the numerical solving part. So that's how it can be useful. Okay, so let's see how we can make use of information like this to simplify problems in certain cases. this is a smooth surface. The block B is at rest and A is moving with velocity. So A makes a head-on perfectly elastic collision with B. Okay. Given that mass of A is, let's say, 5 kilograms and V naught is, let's say, 20 centimeters per second. Find MB, the mass of B, and final velocities after impact. If A's speed drops to 50% of its initial value after impact, it's really a very simple question, but you can see that the interpretation can be a little tricky and you can miss out something if you're not careful. Okay, so just keep in mind what we discussed about the second special case, and hopefully you will be alert to the situation over here. Okay, the second case that we are discussing about. So just try this out, people will discuss. Yes, Siddharth, the answers you have sent me are for the masses of B in the two cases. Just a minute. I will not be able to hear you. Yeah, go ahead. Yeah, so you sent me the answers for the masses. Yes, that's correct. That's correct. Okay, so notice I said there are two cases, and Siddharth has also sent me two answers. So the reason for that is very simple, that the question is giving you information about A's final speed, but it is ambiguous about the direction. So you have to take both the cases into account. Yes, very good, Janvi, that's correct. Okay. So there are both the possibilities which you must have taken into consideration, that A could recoil with a recoil speed of this much, 10 centimeters per second. So with sign convention, V1 will be taken as minus 10, or A could continue in the same direction. So with sign convention, we will take it as.
Sir, I think we did this question in the last class.
We did this type of question. Yeah? Okay.
Yes, sir.
So then though you should be able to do this very fast. Okay. Somehow I missed it from the notes that we've done this. Anyway, so let's see what is the fastest way we can do the question. If you know A speed, you know B speed equally easily, because you just use the concept that E is equal to 1. So you don't need to do any calculation by formula and all that. And then you can just apply the momentum conservation thing to get the mass. Or you can use the formula to get the mass. But you can get the velocities by just using the fact that E is equal to 1. So what is happening here? E is impacting with a speed of 20 centimeters per second. So that's our approach velocity, because B is at rest. So our approach velocity is 20 centimeters per second. It is given that E is equal to 1. Okay. Also given that magnitude of VA after impact is 10 centimeters per second. So that means VA can be in general plus or minus 10. So we'll take the two cases. If mass of A is lighter than mass of B, then after impact A should recoil at 10 centimeters per second. And B will have some velocity like this. So in this case, the separation velocity will become VV plus 10. And that should be equal to the approach velocity. That should be 20. So that means VV will become plus 10 centimeters per second. And once we get this, we can get the mass. Actually, mass we can get from just VA only. And the other case, MA could be greater than MB, in which case, this is what is happening. Going in the same direction at 10 centimeters per second. But in this case, what will be B's speed? It will have to be 30, because the separation velocity is 30, is 20. So this will be in this case VB minus 10, and that should be equal to 20. So this will show me that VB is plus 30 centimeters per second in this particular case. So there are these two possibilities for VB. Now accordingly, I can just use the formula that VA, which is minus 10, is MA minus MB upon MA plus MB plus 20. Now here, VA, which is plus 10, is so from that I can get the mass ratios. Okay, so this will tell us that MA minus MB upon MA plus MB is minus half, or if we assume that MB is N times MA, then N minus 1 upon N plus 1 is half. So N is how much now? So N is 3. So mass of B will be 3 times mass of B. Whereas here, if we assume that MA is, let's say, N times MB. So N minus 1 upon N plus 1 is again half. So n is again 3. So this time it means that mass of P is 1/3 the mass of P. So these are the two possibilities for the masses. And accordingly, these are the two possibilities for the velocity. (15 kg and 5/3 kg). So you have to really look out for all the possible cases that can occur in a question like this when it comes as a multiple choice question, more than one option, MCQ at the JEE advanced level. Be very careful of those type of questions.
Okay, sir.
Very easy to miss out any of the cases. Okay, let's come back to it now. So now we'll come back to the situation of the collision of a particle with a rigid fixed surface.
So we've done that.
Yes, so we'll look at cases of that. Yes. So we had seen both of them, oblique as well as normal impact, right?
Yes, sir.
Okay. A rigid fixed surface. So I will just do a quick recap of the oblique case, and that can include the normal impact case as a special situation, okay, where theta is 0. The approach velocity is the actual velocity. So if the particle has an impact velocity of v naught like this, but it is at an angle of incidence, so to speak, of theta like this. Okay. So at the point of impact, if you draw normal, then this angle is theta, and the speed with which it is impacting is like this. And after impact, suppose the particle goes off in a direction like this, such that the velocity is v, and this so-called angle of reflection is phi. So what we saw here is that the tangential component is conserved, because the impulse is going to be only normal. The impulse is going to be in the normal direction. So tangential component of momentum is conserved. The particle has a mass m. So that tells us here that v sine phi is equal to v sine theta, irrespective of whatever value of coefficient of friction. Whereas the coefficient of restitution is the ratio of separation velocity upon approach velocity. So that is v cos phi upon v naught cos theta. So the approach velocity is the normal component of this velocity v naught. Okay? Because you can see that if the distance between the particle and the surface is x, then the approach velocity is minus dx by dt, which is v naught cos theta. Similarly, at some point of time, if the distance afterwards has increased to x prime, so you can see that plus of dx prime by dt, that is the separation velocity, and that is simply v cos phi. That's how this ratio comes about. So this is now telling us the other component of velocity, that v cos phi after impact is p times v naught cos theta. So if we take this as the x and y axis, suppose, so y is the tangential axis, x is the normal axis, then we can see that before impact, the velocity is like this: normal component, tangential component. After impact, the final velocity becomes minus e times the normal component. So the normal component reverses in direction and gets multiplied by a factor of e, whereas the tangential component remains undisturbed. And now this thing only is our minus v cos phi, and this thing only is our minus v cos sine phi. So from these two, we can also see that v is square root of, actually take v naught common, square root of e square cos square phi, sorry, cos square theta plus sine square theta, and phi is tan inverse of tan theta by e.
So shouldn't it be minus v sine phi? Sir, that
The tangential component is conserved. No? Oh, sorry, this one you are saying, no? Plus one, actually.
yes, sir.
That's plus one, that's correct. This v naught sine theta is the same thing as v sine phi. Whereas v cos phi is the same thing as e v naught cos theta. But vectorially it's in the opposite direction, so the minus sign comes, right?
Yes, sir.
Okay. So now also, if you look at this in terms of the special cases, you can see that E equal to 1 will mean that V is equal to V naught and theta is equal to phi. So it is very reminiscent of a mirror image reflection. So this has nothing to do with reflection, because as we'll study geometrical optics later, you will see that reflection is actually a wave phenomenon. It is because of the wave nature of light. It's not like particles of light are colliding. Light does not consist of particles in the classical sense, because particles must have rest mass. Light, if at all, if you think of light as objects moving, which have momentum and energy, they are photons. So photons are very different to classical particles. Photons are packets of energy which have zero rest mass, but which have momentum and energy. So technically they are called quantum or quanta of electromagnetic energy. But anyway, we can liken it to something like the reflection situation, because the angle of incidence is equal to angle of reflection. That thing. Okay, if E is between 0 and 1, so it is that general inelastic situation, then you will see that V will become less than V naught, but it will at the same time be greater than V naught cos theta. It will be greater than the approach velocity, because there will be some tangential component, and your phi will be greater than theta, but it will be less than pi by 2. Which basically looks like the diagram I've made over here, the above one. You can see phi is greater than theta, but it's not 90 degrees. So the particle is not sticking to the wall and moving along it. That is the special case when E is equal to 0. So in this case, what happens is that the particle sticks to the wall, moving only tangentially on it, or sticks to the surface with only the tangential component or the parallel component of velocity, that is your V naught sine theta. And the normal component of velocity is 0. It's not bouncing off. So its separation velocity becomes 0. So this special case, E is equal to 0, is when the separation velocity becomes 0. So that means our phi becomes pi by 2, and the particle sticks to the wall. By sticks, we don't mean it becomes stationary, but it does not bounce off the wall, sticks to the wall or the surface, sliding along it tangentially. At V naught sine theta, immediately after the impact. Then, of course, there might be friction and other things might come into play, but just after impact, if you look at the velocity of the particle, it will become parallel to the wall or tangential to the wall and equal to V naught sine theta in magnitude. So needless to say, this involves maximum loss in kinetic energy, or maximum absorption of kinetic energy, or dissipation of kinetic energy. This involves certain amount of loss of kinetic energy. And this involves zero loss of kinetic energy, because the speed is the same.
Sir, I have a doubt. So in the
Yes.
middle part where E is less than 1 greater than 0.
Yes.
How did you get this, sir? What's written?
That is from the above equations. So you can see that if E is less than 1, then your x component of velocity has reduced whereas your y component of velocity has remained the same, right?
Yes, sir.
So v is less than v naught, but at the same time your y component is not 0.
Yes, sir.
So your velocity will be more than v naught sine theta, not cos theta. It will be greater than v naught sine theta. It will be more than the tangential component because there will be some separation velocity. It won't be 0. Whereas in the third case, your v actually becomes v naught sine theta.
Okay, sir.
Yeah, so just make a correction that it should be greater than v naught sine theta, not v naught cos theta. And why phi is greater than theta? Because you can see from this formula. Here what is happening, if E is less than 0, less than 1, okay, then your tan phi is greater than tan theta. No?
Yes, sir.
Or if you just think vectorially, if you compare the two vectors, the v vector and the v naught vector, the x component has become shorter, whereas the y component is remaining the same. So that means the angle has increased with respect to the normal.
Sir, this one I didn't get.
This vector v naught, it has some x component like this and some y component like this. Okay, so this is your v naught. So this is your theta. In comparison to that, what is happening to your v vector? The x component is becoming shorter, whereas the y component is the same.
Yes, sir, I got it.
So now you can see the angle of inclination would have increased. Phi would have increased. And in the extreme case where E is equal to 0, that phi is increased all the way to 90 degrees because that particle is stuck to the wall and moving tangentially. Okay, so this whole scenario actually leads to very interesting problems where JEE is going to test you on everything from your kinematics basics like projectile motion and all that, right up to your knowledge of impulse momentum and application of collision theory. Okay. So all those reference books analysis of JEE that projectile motion has never been asked in the last 15 years or something. That is completely wrong because there are several questions involving collisions where to begin the problem, you have to know the basics of projectile motion. If you've forgotten the formula or the basic method of analysis of projectile motion, you cannot proceed with those questions. Though those questions will come under the head of system of particles and not under the chapter of projectile motion. But it's equally important. Okay, so that's something that we always have to keep in mind, that the JEE advanced exam especially is such that you virtually it does not leave anything out at all. You have to be sure of at least the basics in everything, in all parts of physics, chemistry, and maths. So let's look at an example. So here what is happening is we are firing a projectile at an initial speed of 50 meters per second at an angle of 37 degrees. But there is a vertical wall which is at a distance of, so this distance is, let us say, so this distance is 180 meters. So we want to first of all find the time of impact. And velocity of impact. Then we want to find the velocity just after impact. If E is equal to 1, if E is equal to 0.4. And third, we want to find the position at which the particle hits the floor after impact. Okay, if once again, take the two cases, E is equal to 1 and E is equal to 0.4. Take the value of G as standard value of 10 meters per second square. And for your vector analysis, we have to take x-axis horizontally in this direction, y-axis vertically in this direction.
What is the other method of showing that phi greater than theta?
Other method is better just algebraically. Like if you compare the two equations, that your v cos phi is e v naught cos theta in magnitude, right?
Yes, sir.
And your v sin phi is equal to v naught sin theta. So that's why we got the formula that phi is tan inverse of tan theta by e. Now in that, if you put e as less than 1, that means your tan phi is greater than tan theta. So phi is greater than theta.
Yes, sir.
Okay. Now solve this projectile one. So you will see that because the wall is vertical, therefore what is the normal component of velocity when it impacts? It is the horizontal component of velocity. Whereas what is the tangential component of velocity at impact point? It is going to be whatever the vertical or y component of the projectile's velocity is going to be. So the distance of the wall is given to you, the horizontal distance from the point of projection. So you have to use that fact that how much time it takes to reach the wall. From that, you will get the velocity in vector form when it comes to the wall, when it's impacting the wall. And from that, you know what is your normal component and what is your tangential component, and then you use the collision theory. If it is perfectly elastic, then the normal component is just reversed in direction. Magnitude is same. If it is E equal to 0.2, then the X component will reverse in direction and become 1/5 of the initial value because it will get multiplied by the factor of E equal to 0.2. The last part will be very interesting where you are locating the point at which the collision occurs again with the flow. That is after impacting the wall, it comes back to the floor. So where that occurs, where it returns at what distance. Okay, so anybody figured out how much time the collision is taking? After how much time the collision with the wall is taking?
4.5 seconds.
4.5.
Yes, very good. That's correct, Siddharth. So can you tell me, is the particle on the way up when it collides, or is it on the way down?
Down.
Way down.
Okay, so let me work out the initial part. Pick up this whole diagram and
So for the third part, are the answers 60 and 24?
okay, so now let's look at the components, because the easiest way, my opinion, of solving any projectile motion is always to use the components. Just a minute. Yeah, so easiest way is to use the components, as I said. So the initial velocity is x component. Okay, is going to be 40, and the initial velocity is y component. Is going to be 30. So from this we can see that the x displacement of the projectile as a function of time is 40t. The y displacement is 30t minus 5t square. From this we can see that the time of flight is going to be 6 seconds and the range is going to be 240 meters. So definitely it hits the wall, because the range is greater than 180 meters. So that's one thing we know. So now let's come to one more thing, that if it hits the wall at t equal to how much time? The x is equal to t, that is, it collides with the wall. So from that we'll get that time as so you can see. So one more thing you can see, that d is greater than r by 2. So it will collide on the way down. That thing we can already see. So this time when it collides, this time is greater than t by 2. So it collides on the way down. That's just helping us visualize the problem a little bit more. That as the particle it sets off into projectile motion, it has achieved the maximum height already before reaching that collision point. And somewhere here it collides. So the impact velocity, let's say that is Vi. So impact velocity that will be, so our Vx as a function of time will remain 40 meters per second. But Vy as a function of time will be 30 minus 10t. So this will be 40 I cap minus कितना हो जाएगा 15, is it? J cap. So in this impact velocity, this is the tangential component and this is the normal component. So the approach velocity of impact is 40 and the tangential component is 15. So after impact, what will happen is that you'll have a velocity just after impact, let's say of Vf like this. So just after impact, the velocity, let's say Vf, is going to be minus 40 into E, whatever the value of E is, I cap, but minus 15 J cap. And this collision here has occurred, let's say at a specific time t equal to t1. So that is this time t. At this time. So now we have to solve in each of these cases where it lands over here. So you can see for the second part, if E is equal to 1, then the velocity just after impact is minus 40 I cap minus 15 J cap. If E is equal to 0.2, then the velocity just after impact is minus 8 I cap minus 15 J cap. So this is the first thing, the time of impact, the velocity of impact. These things are solved.
The E is 0.4.
That's a 0.4.
Yes,
Yeah. Okay. So then that will be minus 16, right?
Yes, sir.
Correction. Yes, very good, Siddharth. That's correct. Your answer to the third part, where it lands on the ground for perfectly elastic collision, is correct. And the second part is also correct, Janvi. Yes, both answers are correct. Yes, Siddharth, your other answer is also correct. Okay, now Siddharth and Janvi, can you tell me what is the key to solving this part? Like the position that you got, how did you come to the realization of the answer? What were
So
the
we'll
steps? Yeah.
the y component constant, then we'll see how the what's the new x velocity, in the x direction. And then we'll find the time it takes to fall down and multiply
Yes.
the time with vx.
Okay, so basically you wanted to multiply that minus Vx with the remaining time, right?
Yes, sir.
No, from the collision onwards to the ground. Now, how did you calculate that remaining time,
So for
Janvi?
e is equal to 1, it's going to remain the same, the projectile motion. The time will be the same. Or the other e, the time I found by, so it should be minus 30 at the end. And
The remaining time, you mean? Or the time when it hits the ground, how much it came out to be?
sorry, sir.
At what time it's hitting the ground? Like the collision is happening at time t1, which is 4.5 seconds, right?
Yes, sir.
At what time it is hitting the ground?
So t is equal to 6.
In both the cases?
Yes, sir, it should.
Yes, okay, that is the key. That's the same thing that you are also saying, Siddharth, right? Okay. Now the thing is, can I look at the question directly and say that the time will be 6 seconds in both the cases?
Yes, sir.
Or so how will you come to that realization that the collision does not affect the time of flight? Is that a correct statement?
Yes, sir, because Vy is not affected now by the collision at all.
Yes, very good. Because the vertical component of motion is not affected by the collision, no? Because the collision impulse is along the horizontal direction. Okay, so this is the most important thing to realize over here, that the collision is with a vertical surface, with a vertical wall. Okay. So irrespective of what the value of E is, that means that the collision impulse, okay, J, is horizontal. In fact, J is, if you look at it vectorially, it is minus of M into that E times Ux minus or plus Ux, like this, where Ux is 40 meters per second, like this, I cap. This is a collision impulse. If you need to calculate it, you will calculate it this way. Right? So the fact that it is horizontal, that means it does not affect. So the collision does not affect the vertical part of the motion. Does not impact in any way what is happening along the y-axis. The vertical component of motion dictated by these two equations, that y is equal to 30t minus 5t square, and y component of velocity is 30 minus 10t. So therefore, collision occurs at t equal to t1, which is 4.5 seconds. Okay, and finally, the ball hits ground again. T equal to capital T, which is 6 seconds. So from impact to ground, the time is capital T minus T1, which is 1.5 seconds. Okay. So now we can go back to the diagram and we can understand that if this hits so if this comes and hits the wall at a time t1, and then from there it continues on its journey like this. So it hits the ground at time capital T. So this distance, let's say, is something, let's say it's capital D. So this capital D will be E times Ux into that remaining time. Right? So For E equal to 1, that distance will come out to be 60 meters. For E equal to 0.4, that distance will come out to be 24 meters. Or you can also reference it from the starting point. So in one case, it will be at 120 meters from the starting point. In the other case, it will be at what is it? 156 meters from the starting point. Okay, so this was an important thing to understand. In order to be able to solve the question within a feasible amount of time, that I don't need to recalculate what is happening along the y-axis, that at what height it has hit the wall, so therefore how much vertical displacement from the collision till it hits the ground, then what is the vertical component of velocity and all that. I don't need to recalculate all that kinematics. I should just understand that, if the regular projectile motion had been like this, now in the case of the collision affecting it, the wall is somewhere here. So in the case when E is equal to 1, this will be just like a mirror image. So if this was 180 and the original range without the wall would have been 240, it's easy to understand why this will be 60. But in the case of the E equal to 0.4, the motion after the impact is somewhat, you can say, truncated, because it loses some kinetic energy. So if this point, so after impact is going to have a much smaller x component of velocity. So this distance, capital D, will become E times range minus V.
Sir, in what chapter do we get those questions where some particles start projectile explode or something?
In this only, explosion is also part of momentum conservation. If a body explodes into multiple parts or multiple fractions, then the momentum is conserved during the explosion, but the energy actually increases, because that is kinetic energy increases, because the the explosion results in some kind of chemical potential energy or energy released as heat converted into kinetic energy.
But so why does it explode?
But there is no external force. It explodes because of a spontaneous chemical reaction that happens. What's my point?
And so that energy converts to kinetic energy.
Yes, yes. So in that, the spontaneous chemical energy released in the form of combustion. So heat it's a reverse situation. Instead of kinetic energy dissipating into heat, like happens in the case of inelastic collision impulses. But in the case of explosion, the forces that act on the fragments because of the explosion, they result in conversion of heat or other forms of chemical potential energy into kinetic energy. So kinetic energy of the system increases as the momentum remains conserved, because there's no external force during the explosion that is occurring.
Okay, sir.
So that will also come in this only. It will come as an application type of question. Have you done that very interesting question in HC Verma where a person jumps off a cliff holding onto a suitcase or a bag, and then as he is in vertical free fall, he throws the bag at some stage to go into projectile motion?
No, sir.
Okay, so there is it's very interesting type of question. So there also we apply the similar kind of principle we would have applied to an exploding object while it is in free fall. But only here, instead of exploding, the person actually throws an object from it. So there's a person standing at the top of a cliff with a bag. So the mass of the bag is small, and let's say, and the mass of the person is m. Now he just steps off the cliff. But when he is at a certain position, what he does is he throws the bag with a certain speed, let's say, u. So that gives him a recoil speed, let's say, u prime. And as a result of that, his path becomes like this, and the bag's path becomes like this, and he ends up falling safe. You'll find this exact diagram in HCV. Do this question. So this is very much like that only. You can see that if you see the bag plus person as a system, okay, the horizontal momentum will be conserved. Even while they are in free fall. So gravity is acting on that system. So vertical momentum cannot be conserved. So minus m into v naught plus capital M into u prime or v prime whatever should be 0. But along with that, they have this vertical component of velocity v1. Okay, so from there, the projectile motion starts.
Sir, in the HCV, this is a building and there's a pond you want to fall into when it
Yes,
is
yes. There's a pond over here. This distance is given to you, this height is given to you out there. And the height at which he throws the bag, that is also, or it's asked probably that at what height he should throw the bag or something like that. So, this is a similar situation that you are saying. The same way of solving we will do when we come to exploding projectiles also. You can treat this like an object in free fall, which explodes into two fragments.
Yes, sir.
Anyway, so for the moment, let's come back to this collisions. Okay. Now we'll see one more thing here, one more example to conclude this section before we move on to oblique collisions, which will be the final part of collisions. And then we're not done with the chapter. We will look at again some more general applications of momentum conservation and impulse momentum theorem, etc. And then of course we have to also look at variable mass systems. Okay, so long way to go in this chapter. But yes, collisions is a very big part of it. So, very big fragment of it. So anyhow, let's look at this situation where instead of a projectile colliding with a wall, it is bouncing repeatedly. So this time, let us say we have projected it with a speed of quite a high speed of 100 meters per second at an angle of projection of, let's say, 53 degrees. So it goes like this, then bounces, then bounces, then bounces like this. So it is given that after the first impact, the maximum height between first and second impact. So that maximum height is h1 equal to, let's say, h by 2, where h is equal to u square sine square theta by 2g, or in this case, that will be in 240 meters. So from that, we have to find the coefficient of restitution for the bounces. R1, R2, and a general formula for Rn, where each of these is range from first to second bounce. R2 is range from second to third. Like that, Rn is the general range from nth to n plus 1 bounce. Okay, so let's work this out. Sorry, this will not be 240. This will be 310. Take GS 10. Yes, very good, Siddharth. Your value of E is correct. Janvi, I'll just check your answer for. You sent the answer for range, is it, or for E?
For E.
No, just check your calculation once more. Yes, Aryan, your answer is correct for E. Okay, so now I'll just give you a hint about something that occurs in this kind of situation. See if you can use that to solve this question more effectively. So remember that a projectile is a combination of horizontal and vertical motion. Whereas in this case, the collision with the ground is happening in such a way that the vertical component of the velocity is the normal component and horizontal is tangential. So if you look at a situation where we have pure vertical motion, let's say. Okay. So if an object is dropped from a height h, so it impacts the ground for the first time with a velocity of √2 gh. So then immediately after impact, after the first impact, it has a velocity, let's say v1. So v1 becomes e times v1. So now the maximum height it goes to before it comes back and makes the second impact. Let's say that is h1. So that interestingly becomes e squared times h. So now if we apply this information to a projectile, we'll realize something that if you projected something at u at an angle theta such that this component is ux and this component is uy. So before it makes the first impact, it has a range r and a maximum height h. So that maximum height is uy square by 2g, and that range is ux into time. So it is ux into 2uy by g. Now, after making the first impact, when it has got some new velocity, let's say u prime at some new angle, so that ux prime is equal to ux, it remains the same. But uy prime after the impact becomes e times uy. So because of that, what happens is that between the first and second impact, if you look at all this, you get the result that h1 is equal to e square times h, whereas r1 is e times r. So this series progresses. h2 is equal to e to the power 4h. r2 is equal to e square r. Like that, the series progresses that so see if you can utilize this information effectively here.
So the x component of the
Because
velocity.
for the first impact, the impact velocity is ux I cap minus uy g cap. So after impact, the velocity, let's say v prime, is same ux but plus e times uy g cap. So because of this only all this happens.
So how did you get R1 is equal to E times of R?
Yes, once I had just got disconnected. So anyway, let's continue with that question. So I think all of you would have understood it by now that using this concept, yes, yes, Jani.
Then how did you get R1 is equal to ER?
Because see what is happening in a projectile, you have to understand how each of these quantities are affected by Ux and Uy. Okay, so your maximum height is Uy square by 2g, whereas your range is Ux into time of flight, which is
Yes, sir.
into
To U
by g,
by G.
and time is similarly 2Uy by g. So what is happening is after the first impact, your Ux remains the same, but your Uy becomes E times the earlier value. That's why the height becomes E square times, whereas the range becomes E times. And the time also between the first and second impact then will become E times the earlier time. So then the next impact that will happen, this will become the same as Ux prime, which is Ux, but this will become E times Uy prime, which means it will become E square times Uy. That means your new height will now become E square times this height, or E to the power 4 times the original height, like that. So that's how the series progresses. This clear, no?
Yes, sir.
Okay. So that's how you can see that as it goes from impact to impact. This is your original range and original height. So between first and second impact, then between second and third impact, and so on and so forth. So this was our original U with Ux and Uy at that point. So using this, if you solve this previous question, using this analysis, you will see that the result you are getting is like this, that you use these values here, your H will come out to be 320 meters, and your original range will come out to be 60 into 16, right?
So 240. No, sir, no.
Hey, this is a different case.
960.
Ux कितना है 60 है, and time of flight कितना है 2Uy by g is 2 times 80 by 10, so 16, right? So this correct, this calculation? So
Yes, sir, 960 it would get.
960 meters, okay. So that is why now if this is our H1 and this is R1, so we will see that H1 is equal to E square times H. So we've been given that now H1 according to this is 160. So E square is equal to 1 by 2. So E is equal to 1 by root 2, or approximately 0.7. So that is why H1 will be H by 2, means that R1 will be R by root 2, or approximately 0.7 times R. Then our H2 will be H by 4, and R2 will be R by 2, like that. So our Hn will be H upon 2 to the power n, whereas our Rn will be H upon root 2 to the power n. So we can write that as 2 to the power n by 2. This will be the general formula. So this is R in the denominator. Okay, so this will be in general 320 divided by 2 to the power n. And this will be in general 960 divided by root 2 to the power n, or 2 to the power n by 2.
So noted.
Right, so this is another trick to remember for solving these type of questions. Okay, now next section we will see is oblique collision of two particles or two bodies. Instead of oblique collision of a particle with a rigid surface, rigid and fixed surface, now it's two objects or two bodies or two particles, but they are not making a head-on collision, which means that the collision impulse is not along the same line, or the line of impact is not along the direction of initial velocity. So oblique collisions of two bodies or particles. So in this, the first specific example we will take is when the second particle or body is at rest. So we take the example of a moving body colliding with a stationary object. Obliquely. So now also for the purpose of this example, let us imagine that the colliding bodies are like basically like discs which are kept on a horizontal surface, and we are seeing the top surface, the top view of these discs. So some situation like this. So let's say this is body A and this is our body B, and this is at rest initially, whereas body A is moving with a velocity vector which looks like this. So this is the situation before impact. Okay, so as they come in contact, what will happen is that you will see the line of impact is not going to be along the line of the velocity vector v1. It's going to be a different line of impact. Hence, the final momenta will be in different directions. So let's say now we are observing them coming in contact. So as they come in contact, okay. So this is our center to center line. So because they are two disc-shaped objects, so as they come in contact, the plane of contact is the tangent plane. So the collision force which will act normal to that tangent plane. This is the center of this second disc. This is the center of the first disc. So they will experience collision forces or collision impulse, which will be like this. This is the impulse on A because of B, and this is the impulse on B because of B. Okay, so this kind of impulse acts. And as a result of this kind of impulse acting, what happens is that after the impact, this is during the impact or during contact, what happens is that this object goes off with a velocity Vp, which will be along that line of impact. Whereas this will go off with some velocity Va, which is at some angle with respect to it. So if this was our original direction of V0, let's say this angle is alpha, this angle is beta. This angle is alpha. This is the line along which this one traveled before coming in contact. So what we will have here is momentum conservation of the system, but that will be a two-dimensional equation. So ma into that velocity v0 will be equal to ma va plus mbv. So if we look at this equation now, it will convert to two component equations. So like two equations that we are getting. Now, as you can see that we have quite a few unknowns. Assuming that MA and MB are known quantities and V0 is a known quantity. So we have four unknowns. So now one more equation, the value of alpha is going to be determined from the geometry of the impact. So some information will be given about this. So one more equation will be determined from that. The value of this angle alpha, that is, if you see angle alpha is the angle of the line of impact, that is the axis of the collision impulses. With respect to the initial velocity of this one. So that angle is alpha. So the line made between the line of impact versus the initial velocity vector of the body that is coming and colliding with the stationary one. So that angle alpha is as per some kind of geometrical information which has to come from the situation of the collision. So one more equation will be generated from that. And now you'll notice we still need one more equation because we have four unknowns. Okay? So momentum conservation is giving us in principle two equations. Some geometrical information which will give us the value of alpha. So that's one more equation that we get from that. But we still need a fourth equation, and that fourth equation will come from the coefficient of restitution. And using the fact that approach velocity is equal to E times surface velocity. So we'll discuss about that next. But first, move down to this point. Okay, so now let's determine how we get the coefficient of restitution involved in this whole business. Okay. Okay, so that one equation that will come in terms of coefficient of restitution. So I'm drawing a kind of magnified diagram of the situation just before impact and just after impact. So just before impact, as they're just about to come in contact, you can see at that point of time, A has a velocity in this direction, which is making what angle with the center to center line. It's making an angle alpha. We're taking this angle as alpha. So what is the approach velocity here? The approach velocity of A towards B is B naught cos alpha. This is the component of V naught towards B's center. That one. This object is moving at V naught like this, and B's center is over here. Then we need to find the component of V naught towards B's center, and that is where the angle alpha comes in, because this angle is alpha. Whereas just after impact, so just before impact, just after, what is happening is that B has a velocity of VB in this direction, which is directly along the center to center line. So the separation velocity, the contribution from B is directly VB, but A is having a velocity which is in this sort of direction. Let's say like this, okay, where this angle is beta, and earlier we saw that this angle was alpha. So now taking this into account, you can see what is separation velocity going to be here. It is going to be VB minus VA of cos alpha plus beta. So this is the separation velocity.
So alpha,
Okay.
alpha
This
plus
whole
beta.
term now is the component of VA, again towards B center. Okay, and note one thing, that this term cos alpha plus beta can become a negative quantity if alpha plus beta is greater than 90 degrees, which looks very likely in this case over here. So it's actually going to be VB plus some term, because that cos of alpha plus beta is going to be a negative quantity. So now the idea becomes like this, that, so don't think of this like a formula, just think of this conceptually. So our separation velocity has to be equal to E times our approach velocity. So this is the fourth thing we'll consider while solving a collision of this type. This is like the third thing we'll consider. Okay, so people, we'll conclude today's session here. We have another session coming up within the next 2 days, I think day after tomorrow or something. So try to finish up all questions related to collision of particle with rigid surface, one-dimensional collisions, conservation of linear momentum examples before that, and also center of mass by application of integration. In the next lecture, we will look at this kind of situation, oblique collision of two bodies in more detail. And of course, here we've seen one case where the second body is at rest, but we can always have an oblique collision where the second body is also in motion. Okay. So we'll look at all that in more detail and we'll wind up collisions in the next lecture. If time remains, then we'll also see some examples of center of mass by integration in the next lecture. Some like numerical examples or some more tricky type of situations there. And then after that, there's more work in center of mass. We still have to do variable mass systems and then explosions and things like that. So a few more lectures remaining before we can conclude this and move on to rotational mechanics. So anyhow, that's it for today's session, people. Wish you all the best and have a nice day.
Bye, sir. Thank you, sir.
Bye.
Bye. Thanks.
Thank you, sir.